Hello everyone and welcome. Today we are going to start a new chapter. This chapter is about work and energy. So our first topic for today, we are going to talk about work. So when you hear the word work, you think of a job that you have to go to or an essay that you must write. But actually for us physicists, it has a precise meaning. For us, it means that work is done whenever a force causes an object to move. So to apply work or for work to be done, there must be a force and the object must move due to this force. Work means spending energy. So work and energy are very alike. They are always connected to each other. So whenever you do work, you are spending energy. And we know that the unit of energy is joules. Finally, I can say that I will spend 1 joule of energy if a force, which is equal to 1 Newton, moves an object a distance of 1 meter. But it's very important to keep in mind that the force and the moving distance must be in the same direction. So the movement must be in the direction of the force. So let's start out simple and look at this example here. We have a simple box and we applied a force equal to 10 newtons on it. The box moved to a distance equal to 5 meters. I can simply say that the work done on this box is equal to the distance multiplied by the force. And since the force and the distance or the object moves at the same direction of the force, we can simply say that it's 5 multiplied by 10, which is equal to 50 joules. So the unit of work is the same as unit of energy, which is 50 joules. But what would happen if I had an inclined force? So the force in this case is not in the same direction of the movement as we agreed on. We said that the movement and the force must be in the same direction. For example, this box right here, it has a force applied on it. It's inclined. It's neither in the x direction or in the y direction. In this case, we must divide the force into two components. Some of you already know how to do that, but we are going to talk about it from scratch. So it must be divided into an x component and a y component, okay? But how do I do that? The steps to do that are the following. How do I divide the force into an x component and a y component? First of all, I will need something called the inclination angle, okay? Look at it here. The inclination angle is the angle between the horizontal and the force itself. The second step, I can say that the force which is horizontal or going in the x direction will be equal to the force multiplied by cosine of the inclination angle. And as I said before, some of you already know this. I will find the x component of the force by multiplying the force with cosine of the inclination angle. Let's call it theta. Now, the vertical force will be F multiplied by sine of theta. So, if the object moved horizontally, I will say that the work in this case done will be equal to force cosine theta multiplied by d, which is the distance that the object moved. So that is simply work. So let's do some questions to make sure that everything is under control. Question number 1. A joule is equivalent to Newton multiplied by meter, Newton multiplied by second, Newton divided by meter, Newton divided by second. Well, I know that work is equal to the force multiplied by the distance. And the unit of force is newtons and the unit of distance is meters. And we already know that the unit of work is joules. So I can say that 1 joule is equal to Newton multiplied by meter. So the answer in this case is simply A. Question number 2. The magnitude of work done against friction to slide a box in a straight line across a uniform horizontal floor depends mostly on, first of all, the time taken to move the box, second of all, the distance the box moved, the speed of the box, and the direction of the box. Actually, it's not something we ever talked about, so let's take it simple. We know that the work is equal to the force multiplied by the distance. So it's asking me about the magnitude of the work done depends on the following. So we can just forget about this sentence right here. It doesn't really have to do with our question. So the work or the magnitude of the work done depends on the force and the distance the object moved. So does it depend on the time? No. Does it depend on the distance? As we said, yes. It does not depend on the speed, neither the direction of the box's motion. So the answer is simply, in our case, B. Next question. If the person shown on the right slowly raises the box weighing 100 newtons. Again, the box is weighing 100 newtons from the floor to rest at a height of 3 meters. The work done against the gravity is most nearly 30, 50, 150, 300. Okay, let's think it as follows. This is our box. It has a weight equal to 100 newtons. So if I were to raise this box, I would need to apply a force that is slightly larger than the 100 newtons. I must apply a force that is slightly larger than this 100 newtons because I don't want just the force to cancel with the 100 newton. So it must be slightly larger, okay? So we can say that in this case, work is equal to the force multiplied by the distance, okay? Now, it's telling me that the distance the object moved was 3 meters upwards, okay? So it moved 3 meters upwards. So I have the distance, which is equal to 3. And the force, I'm going to assume that it's only 100 newtons, which is equal to the weight. But as we agreed on, it must be slightly larger than 100. So in this case, work is equal to force multiplied by distance, which is equal to 300 newtons. Okay, what is wrong with this inclination angle? Why did we not say that the force must be divided into two forces? Well, here we have a pulley. A pulley's mission is to do the following. It changes the direction of the force. So he's pulling the rope at an inclined angle, but this pulley is changing the direction of the rope to be vertical. And since I'm studying the force on this object, this means that the force is going upwards while the weight is going only downwards. So the force in our case, as we said, must be slightly larger than 100. And since it's going upwards and the force and the movement are in the same direction, so I can just simply say that work is equal to force multiplied by distance. By the way, we're going to be learning a better way to calculate the work done on this object in the future lessons. Question number 4. A 12 kilogram object has initially 24 joules of energy. Okay? What is kinetic energy? We're going to talk about it in detail later. It's the energy of any moving object. Okay? But why are we answering questions about kinetic energy while we didn't cover it yet? Actually, you have to understand that sometimes if you see the word kinetic energy in the question, that doesn't mean that you have to use the kinetic energy equation, which, as I said, we didn't cover yet. So sometimes that can be misleading. You could see kinetic energy, go right forward and write the equation of kinetic energy. Well, that's not the trick. Now, it says, how far will the object move against a net resisting force of 6 newtons? Okay, so I have this object. This object has energy, or in other words, you can say it has work inside it, equal to 24 joules, okay? And it's moving this way. Now, I have a force that is being applied on the other side, which is equal to 6 newtons, trying to stop this object. How far will it move before it stops? Well, the only thing I can do for now is work is equal to force multiplied by the distance. So the energy or the work the object has in it is equal to 24 joules. This is equal to the force multiplied by distance. What is the force trying to stop the work? So force doesn't always have to move the object. Also, force can be done to stop an object. But as you can see, the force and the movement of the object also must be in the same direction. Or let's say, in this case, it's in the opposite direction. But what I mean, if it's in the x-axis or if the movement is in the x-axis, then the force also must be in the x-axis. So going back to our question right here, the force is equal to 6. We multiplied by the distance, which we do not know. So if you want to find the distance, we will divide both sides by 6, and we'll divide this side by 6. So the answer in our case will be 24 divided by 6. So 4 is equal to D. So the distance is 4 meters. So the answer is B. Final question. While riding a chairlift, a 55 kilogram skier is raised a vertical distance of 370 meters. What is the total work done on the skier? And we have these choices. Now, again, this skier is being lifted upwards by a distance equal to 370 meters. Okay? How much work did I do on this man so I was able to raise him this distance? Well, this is pretty similar to the question about the lifting box. This man has a weight. This weight is equal to his mass, which is m multiplied by g. In our case, it's 55 multiplied by approximately 10. Okay, so approximately his weight is 550 newtons. So I will need a force slightly larger than his weight, which is 550. So let's assume that the force in this case is 550 and he's being lifted upwards. So we can say that work is equal to the force multiplied by distance. The force is equal to 550 multiplied by the distance the man was raised, which is 370. The answer will be in this case 2 multiplied by 10 to the power 5. Okay? Now, things will get a lot more clear when we introduce other types of energy, so stay tuned for the next videos for everything to be under control. See you then.